Hi guys, in this video we are going to discuss the problem minimum OR path from starter 73 of CODECHEF. So before I start the problem, I should let you know that this problem doesn't is not that tough. It doesn't require any complex data structures and other stuff like that. Neither any complicated algorithm is required. It just requires a basic like a binary check function or a binary search algorithm sort of a thing. But it requires a observation. So for the people who were able to do it, you must have gotten the observation correct. For the people like me who couldn't, this video would help you. Cool. So the problem states that Heraces has an array A of size n containing non-negative integers. He starts at an index 1 of A. So basically he started at the very first index of the array. So over there they have started with 1. Like if we are taking 0 based indexing, we'll say it's the 0th index, and wants to reach the index n. In one move he can do the following. If he's currently at an index I, then he can move to any index j such that I is less than equal to j and j is less than equal to minimum of I plus ai or n. So definitely he can't exceed the limit of the array, and at most he can travel ai steps from standing at I in the right direction. The cost of a path is defined as the bitwise OR of all the array elements visited by Heraces during his journey from index 1 to index n. So yeah, that's it about the question. If it's not possible to come up with a path, then we have to print -1, else we have to print the bitwise OR of the minimum path possible. So let's say you are having two paths, one has a bitwise OR equal to 4, the other has a bitwise OR equal to 6, then you will be printing 6 in that 4 in that case. So yeah, that's it about this question. Other than that, they have mentioned the constraints. So the number of test cases is less than 1000. N, which is the number of elements, is less than 10 to 5 into 10 power 5, and A, which is the the element itself, is less than 5 into 10 to the power 5. Also the sum of n won't exceed 5 into 10 to the power 5 itself. However, one special thing to take care over here is, because we'll be doing bitwise operations, and since we'll be using bitwise operation in a loop, so technically 32 would get multiplied by this and the number becomes a bit bigger. So in order to reduce the time complexity by a bit, what we can do over here is that since we are talking about 5 into 10 to the power 5 in total, so we don't need 32 bits to represent that. 20 or 21 bits can easily represent this thing. So we have to limit our bits as well, else it could give a TLE as well. Cool. So let's get started with the question. So the question states that we have an array. Now we'll be starting at the first location. From the first location, let's say this is A1. Let me write it as A1, A2, A3, A4, A5. From the first location, we can move to the right by a amount that is A1. So let's say if A1 equal to 3, then I could have moved to this index or this index or this index, right? If A1 is equal to 2, then I couldn't have moved to this index, but would have limited my reach till here. Now, is there a case where a path won't be possible? Yes, there could be a case. So for example, if we have 101, right, in one step we can move to 0, but now at 0 we don't have any jumps left. Let's call this as jumps, right? The way we are moving to the right. So the jumps makes more sense to me and more intuitive as well. So once we have reached the first index from the 0th index, then we have no jumps left, hence we won't be able to proceed further. Moreover, the element over here itself is 0, so we can't even utilize this to move. So yeah, that's it. So this is one observation, that yes, there are cases wherein no path would be possible, but those are easy to detect. So let's talk about what would be the minimal path. So for that, let's talk about binary numbers. So any number can be represented in a binary format. So for example, this is 4, this is 6, right? A special thing is that when you're representing any number in a binary format, let's say you are having a number 6, right, or let's say you are having a number 4, then if you uh, take all the bits to its right and make them all ones, right? So let's say now we have two numbers. So the first number is 100. In the other number, we have taken all the bits to its right and made them 1. So the other number is basically 1 1, right? Even in this case, this element would be greater than the below element. So what I want to say is that a bit that has a higher priority, or which is of a more significance. So these are basically called MSBs. So the bit, if you want to understand it, you can read about it more. But basically, the bit that is to a left has a more significance, and even if we sum up all the bits to its right, even in that case we won't be able to like match this number. The number still would be smaller. So I hope that makes sense. So what can we say from this logic? So we want to minimize the number of bits that we include that are to the left itself. So for example, if we take a like a bit structure like this, so over here I'm representing, let's see what we are representing. So this is 1 2 4 8 and this is 16. So basically we're representing 20 over here, right? Now what I'm saying is, if I am able to ignore this bit, right, if I'm able to ignore the first bit itself, then the entire value, even if I set everything up, would still be less than 16, right? So this would be 15. So that's what I want to do. I want to minimize the number of bits to the extreme left. So how can I do that? So what I can say is, I have like I'm having 20 bits in total, because I said that the number you are having is 5 into 10 to power 5. So let's try to Google it up. So what is 2 to the power 22? So 2 to the power 22 is a big number. You can reduce it further. You can say 2 to the power 20. So what's 2 to the power 20? 2 to the power 20 is 1, 2, 3, 4, 5, 6. Even that is a million. That's more than what you require, right? So this should work. So back to the point. So we'll only be using 20 bits. Now what we'll do is that we'll go from the most significant bit, or the bit to its left. So if these are the bits that are given to us, let's call it B0, B1, B2, B3, B4. We'll start from the very left, right? So this is the most significant bit. We'll check that if it's possible for us to not have this particular bit in the final answer, right? So I'll start checking from the most significant bit, and I'll check if it's possible. If possible, then I'll add this value to a unordered set or anything. So I'm just keeping a track of all the bits that can actually be like excluded from the answer. So I'll keep a check of unordered set over here. So I'll add it into my set. So let's call it ignore, right? So we are ignoring these bits. So I'll say ignore dot add whatever the bit I was having, or ignore dot insert, whatever works for you in the STL. Cool. Also, when we'll be checking for ignore dot insert, so we'll also have to keep a track, because the number of bits we have already processed. So let's say now I'm processing B2, right? So when I'm processing B2, I've already processed B4 and B3. Now it's possible that I already added B4 into my ignored list, right? So I shouldn't make any such combination in which B4 gets included, because B4 has a more priority or a greater value than B2. And since we want to minimize the result, we wouldn't be adding any bit to its left. To its left. So I'll also make that check. Once I'm done with this, over here I can also say else. If it's not possible for me to come up with a path which doesn't utilizes this bit, right? In that case, I can simply add this into my answer. Now how I'll add it to my answer is, I'll list so the way I'm adding it to my answer is, I'm just ORing the bit value and adding it up, because at the end the answer we require is in terms of OR. Now what about a special case? Is there a special case over here? So yeah, one special case we already discussed it, wherein the path couldn't exist. We can simply check that. Well, I'll go through the algo, I'll discuss that as well. So what about other cases? So another thing is that since we want to go from the index 0 till the index n, so whatever our path is, so it can always be represented by this, right? So these are a number of chains. This could be 0 or more chains, but 0 and n would 0 and n minus 1 actually, yeah, n minus 1. So yeah, 0 and n minus 1 would always be present in my answer. So what I can say is that I can say that, okay, so my result would always contain all the bits from 0 and n. Also, when I'm checking that if it's possible to compute a path that doesn't contains a certain bit, if that bit is set in 0 or n minus 1, that bit has to be there in my answer, irrespective of whether it's getting included within the path or not, right? So I'll ignore that case. So if a bit is set at 0th or n minus 1th location, then I would definitely be having it. have it. So basically I'll ignore my checking for this case. Yeah, that's it. So this is the heart of the question. Now coming to the actual code, like, or the pseudo code, that how would we code the function which checks if a path is possible or not. Now let's talk about that. So in that function I'll be only requiring two information. So what is the what are the ignored bits I'm considering? So ignored bits and the vector itself or the array itself. So what I can do is I can start from the element first, element 0, the element itself. I can go till n. Also I can take a variable jump and I'll initialize to 1. What the reason I'm doing this is because we are actually starting at 0, but I'm assuming I'm starting at -1 and I'm giving it a jump of 1 so that it can come to 0. That won't change anything, but that would just make the code more intuitive and more easier to understand. So over here, as soon as I reach an index, I firstly subtract my jump, right? Because I've already traversed one step in the right direction, so I have to subtract my jump. Now I can check if my jump is less than 0. That means I couldn't have completed the jump initially, because you can't jump. You can't make a jump if you are only left with a single value, right? Or if you are left with 0 jumps, then you cannot make a jump. If that is the case, I can return 0, that this path wasn't possible. If that's not the case, then for all the bits, right, from 1 to 20, since we were considering the numbers from 1 to 20, I'll check that if this bit is set in the current element or the vi. So basically the index is I and the element would be vi. If it's set in this, then in that case I cannot take the help of, I can't take its help, right? Or I don't want to include this in my answer. So now I'll check that if this criteria was met. If this if this criteria said that I cannot take the help, then I can't do anything. But if I can take help, so I'll update my jump. So now my jump would be maximum of the jump I'm already having, or I can take the help of this particular element also, right? So yeah, that does it. Now if we are able to traverse through the entire array, that means that we were able to use only those elements whose bits are allowed, and we were able to traverse through the entire array also. In that case, we can simply return 1. So 1 basically denotes that we were able to make this jump or traverse this array without using the bits that were specified in ignored bits. If that's the case, then it's good enough. If that's not the case, however, then we'll have to delete the current bit that we were setting. Okay, let's go through the code. I think it would make more sense over here. Yeah, so this is the entire code. Let's go step by step. So firstly, I'm just taking the n and v, so the vector and the number of elements itself. Then I'm considering a set called bits ignored. So what bits ignored is saying is that these are the bits that I should not be considering. Now over here, just to save time typing, I used a set of int. You can actually use a vector of a boolean vector, and you can actually save some time complexity as well as space complexity. So this is one thing you can improve. Then what I'm saying is that result would be equal to the OR of the 0th and the n minus 1th element, because they would always be present in the path. I hope this makes sense. Then I'll be going through all the bits. So as I said that I'll be considering only the bits up to 20. So I'm starting from the most significant bit from MSB, or the most significant bit. Cool. Then I'm checking that if my bit was set in the last element or in my 0th element. In that case, I need not check, because this bit has to be there in my final answer also. So I'm ignoring a check over here. Then what I'll do is that I'll add this particular bit that is denoted by B into my bits ignored set, right? Then I'll try that if it's possible to have a path in which we are ignoring all of these bits, right? All of these bits that are denoted by bits ignored. If it's possible, well and good. If it's not possible, so over here I've taken not. If it's not possible, then I have to include this bit in my final answer also. So I'm adding this bit into my final answer, and then I'm also erasing this bit from the bits ignored section, because this bit cannot be ignored, so I have to erase it. That's trivial actually, so you must have understood it. I'm assuming if you couldn't understand this basic stuff, maybe you want to like watch the basic stuff related and required for bit manipulations. Okay, so lastly I'm checking, so there's one case as well where the path isn't possible, right, at all. So if the path isn't possible at all, uh, in that case I'll have to print a -1, right? If a path is possible, then I'll print a result. Going through the possible function, that was returning me a 1 or 1 or a 0 depending on if a path is possible or not. Initially I've started with a jump equal to 1, then I'm decrementing my jump by 1 because I'm already making a jump. Then I'm checking that if this jump was possible or not. If it wasn't possible in the first place, I'll return a 0. Then I'm defining a boolean variable can take jump. So can take jump basically defines that can I use this particular element or the element at the particular location to increase my jump. So I cannot take the help of this particular element at the index I if and only if the current element actually has a bit set or has a bit that has set that is set to 1, which was already which was required not to be used, right? So if I have such a bit that is set in I and that's also available in like ignored section or the ignored bits, then I cannot take the help of this particular element. In that case I'll set the can take jump to false. I can't take its help and I'll break the loop. Then I'll check that if I can take the help, then like make my jump maximum of jump or jump comma I, and at the end if I'm able to make the entire loop or entire traversal, then I'll return 1. Yeah, so that's it. If I show you the code, so yeah, I've coded the exact same thing over here as well. Give me a second. Yep, so over here you can see that it's a AC, but you can also see the time taken. So in this particular case it was 0.6 seconds. I think the upper limit for the time was 1 second. So even a slight of a constant variation can actually land you into a TLE in these two test cases at least. So what I would say is that if you're coding it up, try to not use this set over here. Rather you can actually use a vector bool. So you can actually use a vector bool called bits ignored, and use it for the same thing. By this you will be able to reduce the time complexity as well as the space complexity. Cool. So yeah, that's it for the video. I hope you understood the solution. If you still have any doubts, let me know in the comment section below. Thanks a lot guys.